Hi, everyone. Thanks for the introduction. So I work as a staff applied scientist at LD. The topic for today's talk is solving product substitutions using self-supervised machine learning. Just the main agenda of the talk, we'll just touch on what's the importance of substitutes in the grocery e-commerce, how Loblaw has collected human annotated substitution data over time, and how we can use that data to benchmark the performance of different self-supervised models which we attempt to learn in this experiments. Yeah, so substitute products are goods which can be used interchangeably. They have similar traits. For example, a toothpaste can be by different brands having similar ingredients. So that makes a product substitute. So in person, when we are shopping, it's very, we might not look into it, but it's very easy for us to make decisions on the fly. If a product is not available, we pick another thing. But in in e-commerce shopping, in order to replicate similar experience, we need to have a good substitutions models underneath, or even the ability to collect this annotated data over time. And we started with, currently in Loblaw, we have a substitution model which is running in all our products, especially for PC Express, the topic for today. And that's the process. The idea is to get human labels over time using active learning. So overall, by solving substitutions, we improve the sales by minimizing the impact by out-of-stock orders, improves user experience, and product discoverability, where we can recommend products which are complement substitutes. And the reason this problem is a bit difficult is that we don't have any ground truth, human annotated labels, I would say. We don't have human judgment collected on these substitution products, and the product catalogs can be large. In grocery, it keeps on refreshing as well. Okay. And bad recommendations for substitutions, they can erode trust. There are many tweets, and if a product substitution is not good, it can leave a bad impact. So currently at Loblaw, our substitution workflow is when a user has selected a cart, they have all the items in the cart. There could be some items which are in low stock or out of stock. So when they're about to check out, they're given an option: if this product is not available at certain pickup time or delivery time, can we replace this? And they can select a product from those substitutions, either fully bypass this. And this is how we can also collect human judgments. So the very simple version of our first model, which is running, is it's using lexical similarity from text, which is TF-IDF-based similarity, and pre-trained image representation models, and combining them with some business rules on top, just so that we can get a starting point to serve recommendations and then over time collect data. So this model is running for some time, and then in order to carry out more experiments, we need to have a benchmarking data set so that we can compare different models' performance against that. So when someone places an order on the app for a pick, our colleagues, they pick the order personally and make the cart for someone who's going to come pick up. And in that process, many times when the user has not selected any substitution, they are the ones who make the choice of the substitution. So that has human judgment captured in that, and we have that data that when this product was not available, what did the personal shopper or the Loblaw employee shopper pick substitute for those products. And using this, we curated a goal test set for product substitutions in grocery e-commerce. It took last 18 months of data, and we prepared a data frame in this way that we have an item code. and against it we have a list of items sorted in the order of their popularity of substitution. So we look at, of all the substitutions, what percentage of substitutions happened between this pair and then this pair. This way we have a sorted substitutions for a product based on their popularity. Some of the filters applied on the data, especially just to ensure that the goal test set is representative of good labels. We're not going to use this data for training. The intention is to use them for benchmarking. Yeah. So once this data is curated for the benchmarking purposes, we have 23,000 products, distinct products in that data set. As I explained, like each row is a product ID, and against it, we have the substitute and the popularity score sorted. General products will have more substitutes, and niche products will have less substitutes. That's expected. And this distribution just shows that of our actual catalog. So these are different categories. We wanted to ensure that this goal set is capturing the similar distribution of the actual catalog in terms of percentage items, and it does to a good degree. This is a visual example of how our goal set looks like once it's been prepared. So the leftmost items are given items or actual items, and they are the substitutes. So the way it's looking now is like the second item is the most substituted item for the first item, and then so on. As I said, it's sorted. Yeah, just a few examples. This is on the test set against which we'll measure our experiments. So we did some qualitative evaluation to just ensure it looks good and we can use it. Okay, once we have this goal set prepared, the next, we conducted some experiments, self-supervised experiments to study how can we capture substitution, similar items this way. So in total, in PC Express, we have around 160K items, not including the marketplace. So if you go on PC Express app, other than marketplace, we curated all the items. We have for items you would see we have various fields like ingredients, text, brand name, all those things, and as well as images. And then we carried out these 3 experiments as a baseline model. We used pre-trained BERT, generated BERT embeddings, just as a baseline. No fine-tuning done on it, just that. And then we did mass language modeling by using Roberta, and we trained our own custom tokenizer as well. And then for image representations, we used contrastive learning algorithm called SimClear. It's a paper by Jeffrey Hinton, simple framework for learning contrastive representations. Yeah. Okay, so starting from mass language modeling, there are 2 ways to do mass language modeling on transformers. We personally use Hugging Face library, but one way is you take a pre-trained model, a language model, and attach a masking LM head on top and continue training it. So that, on the left side, that's called domain adaptation, I would say. And the other side, other way to train a language model from scratch is that we train our own tokenizer first on our data, which is fitted on our kind of text, not like all English language, which we necessarily don't need. And then based on those steps, we create our own transformer architecture in a way that we can modify the number of encoder layers, embedding dimensions, feed-forward layer sizes. And in the first approach, when we just attach an LM head on top of BERT, Roberta, distal BERT, the thing is like the tokenizer is still the same for BERT, and that's been trained on English language. So even with our text, it's going to split them on the training which happened based on BERT. BERT uses word piece tokenizer. We went with Roberta, so that uses BP, byte pair encoding, and we'll get to it. So this is how, for 160K items, we prepared the text. you would see some highlighted tokens. They are special tokens, which we will be using later. In the masking, we don't want these tokens to be masked. And in mass language modeling, a certain percentage of word tokens get masked. And the idea is we learn these associations between categories, brands, how a name associates to a brand, how a category associates to a brand, and vice versa. And then before anything, the first step is to do some normalization on the text, pre-tokenization, and for this, we just did it lowercase. Yeah, as you can see, like all the decimals are split up, digits stay together, but all the punctuations are isolated except for those special tokens. So it's important to ensure that like the special tokens, they don't get separated so that they get treated as one unit in the training. So that's the first process. We did these steps, and we get text like this. Then once we have this text, we can train, okay, I think it's, we can train a tokenizer, and it's a fitted tokenizer. It starts at the byte level, and based on the frequency of our corpus, decides where to split words or not. And when we have retail, grocery, it's very like niche in that area, and we can utilize it. So we trained BP tokenizer using pre-processed text, and we get this kind of trained tokenizer where the vocabulary size is 18,000 of the even a word gets split into smaller words, and that's the token vocabulary size. Special tokens, the first 4 are internal tokens for Roberta, but we have added some our own tokens we'll use in masking. And the maximum sequence length is 60 because we did an analysis and we tokenized all our data and saw different percentiles distribution, and we realized that 99% of percentile data is covered in 60 max sequence length. So we didn't, Bert has 5112, Roberta has 5112, so do we really need that one when we're training from scratch in any way? So these were some choices there. And just to have a comparison between Bert tokenized versus our custom tokenizer, which we have trained, you can see this is the input. That's Bert off the shelf, and it's using word piece tokenizer. So it would split these words like aerosol, whereas our trained tokenizer doesn't split the word aerosol because it happens frequent enough in our retail domain. And it's good for, like, we don't want to split words where we don't need to, and when the vocabulary size is limited to 18K, Roberta has 32K and 50K. Okay, so then comes the point of making the architecture for mass language model, transformer. So just a comparison between the default parameters or Roberta base. So we are using 18K vocabulary. Our maximum sequence length is 62. For that, it's 512. Our output embedding dimension for each learned token later on is 256. They have 768. So we started with a smaller one and see, like, then expand rather than just take 12-layer encoder. And number of attention heads, number of encoder layers, these are like stacked encoders. We just used 4 rather than 12. Intermediate, this is the feed-forward layer size within each encoder. And then Roberta differs from Bert in this way that it does dynamic masking. So we don't need to have like the data prepared beforehand. Rather, when we have prepared a batch, it dynamically masks random tokens with a certain percentage. And so with every epoch, different words would get masked for the same example. We just pass in the corpus. Once this model is trained, we can use, since we have trained this model for mass language modeling, so this is just an inference on that exact task. As you can see, the word after toys, cat toys, is masked, and the model has to predict, and the first prediction is with, which is right. And so this is just a qualitative evaluation of the mass language model trained on this data. Okay, so now then once we have this Roberta model trained, we haven't trained it on any classification task towards categories, but rather we have just trained it on mass language modeling, which has textual categorical information somehow. And when we attach labels of different categories which we internally have, we see some clusters being formed, which is a very good indication that our embedding representations are, they're far apart for dissimilar items, and it's just a qualitative way to evaluate the embeddings. This is a 3D dimensional plot and you can see like clusters, very well-tied clusters formed together. It shows us like the text has a lot of information, especially in grocery data, maybe not in fashion apparel, but especially here. Okay, once this is trained, we have these plots, and then, this is the trained Roberta only. Given those left items, you get these recommendations or the similar items. We are showing the images, but underneath it's using the text data only, just to have a quick evaluation. Okay, some more examples. And we can see like some of the pictures, like the third example, the second, the most similar item is visually very dissimilar, but it must have been textually similar. Okay, so once we have this model using which we have learned the text representations, the next step was we also have images, and we have good quality of images in this way that the background is always white, and it's easy. So we looked into self-supervised algorithms for contrastive learning. So contrastive learning is a self-supervised method where we create augmentations for a given image, contrasting images based on what we want to do. And those pairs get treated as positive labels in that batch, and all the rest of the examples are treated as negative examples. So we don't need any label data. And it's very similar to how a puzzle can be solved as like matching exact animal. So for that, we used SimClear. The full form is a simple framework for contrastive learning of visual representations. It's a paper by Geoffrey Hinton, and it's using, there's a term metric learning, contrastive learning being used. So we take any image encoder, Inception, V3, ResNet, ResNet 15, and that's encoder. Create 2 copies, and the framework is that an original image comes in, we create augmentations, which are positive pairs, and the rest of the batch becomes negative examples. And then the projection head, which is the SimClear head at the end, the loss function in there tries to maximize the similarity between the positive pairs and dissimilarity. So it's going to push apart the images which are not from the same class and bring the positive class labels closer together in the learned space. And in this process, the one thing which we decide or work on is image augmentations, what kind of augmentations we want to create. And there are multiple ones where we can do grayscale as well. You would see we are not doing grayscale. There were some random flip, horizontal flip, but we are doing only these ones because we also don't want to just totally lose color by doing grayscale. And when we're using color jitter as well, it can totally changes colors. So we have certain strengths using which we can give a strength to the color jitters. So these are so when the example comes in, these 2 would be positive pairs, and the rest of the batch becomes negative pairs in the training. Yeah, it's just resuming of training, overall 500 epochs on our data, and we saw that after some time, the SimClear model is converged. And the backbone model or the encoder we are using is ResNet. Once it's trained, we just take that out and we can use it to generate embeddings. Okay. So these are the embedding representations from SimClear. And as you can see, it's not very good at classifying different classes. And that could make sense because products could be visually very similar to each other, and we'll see that, whereas they're totally different. In the textual modeling, we're also capturing categories, so that's better at capturing those things. Okay, now we have 2 models. So these are the neighbors generated by SimClear only. And you'll notice that visually they're similar, but it could vary a lot from, I don't know what that, Yeah, the third example, after Cheerios, you have salami. The second example, you can see like visually, the first two examples look same in the second example, but they're very different products. So how about like we have this text-based representations now and also image-based representations. The next idea is to combine them together. But yeah, that's the next idea. How can we combine them? Now, both are in different latent spaces. One is 512-dimensional vectors, one is 256 and concatenating, it doesn't. So we want to search the nearest neighbors within the learned space for each model. And once we have learned the similarities, then we weigh the similarities by a certain weightage, 0.8 to Roberta, 0.2 to Sinclair, and see how we perform on the goal test set. So to do this, we already established that text representations are better at capturing actual gist of the product. So we use Roberta to generate top 2,000 candidates for each item based on Roberta similarity. Now, once we have these 2,000 candidates, we also get ResNet or Sinclair-based similarities for those items and re-rank those candidates which we have chosen from Roberta. So the first 2,000 candidates, it is a variable number. It's just because of some latency and saving memory. We don't actually need to go all the 160K and generate. So we generate 2,000 candidates from Roberta, re-rank them by Sinclair-based weightages. The metrics which we are using here are two, precision at K, in this way that we have a goal set, and in the goal set, for each item, the number of substitutes can vary. For one item, there are 2, for other, it's 10. So it's tricky to use NDCG or any kind of that metric there. So we are using precision at K, which is looking at the top substitute for an item. And we want to see that in how many recommendations we are able to capture the top substitute from the goal set using these approaches. Mean reciprocal rank is like 1 by the rank, capped at a certain point, which we can do. So this slide captures it all in the results on the goal test set. So on the x-axis, we have K. Since we can generate 160K neighbors, so we need to have an upper cap. So we start with, when we are computing metrics at K equal to 2, we only look at top 2 recommendations and see if it contains the top substitute from the goal set. And it would result in TP or F, true positives, false positives. Okay, so BERT, just with the text, I understand like the text we are using is not very coherent. It's not like, doesn't have the coherence as language does, which BERT is trained on. So we expect it to, it's a flat line at the bottom, that's BERT. And then Sinclair, which is image representations, is that green line, still not great. And then the yellow line is the mass language model, Roberta. At the end, it's the second from the top. Just text. And then these numbers, 0.1, 0.2, 0.3, is the weightage assigned to visual representations or visual similarities. So 0.1 means Roberta has 0.9 weightage assigned to the similarities calculated there, and 0.1 only to Sinclair, and then 0.2. So we notice that as we keep on increasing the weightage of visual representations in this case, the performance keeps declining. And the best we see, I mean, at these data points is that if we just a touch of an image, or just a small weightage assigned to the image, but major weightage to the text representations. And we see like 0.1 there. And like later we have plans, we have a good goal test set which has multiple items. So we can even account for that in our calculations. It's just that we'll, yeah. These are the plots for MRR, but they'll follow a similar trend in terms of performances. Okay. Yeah, so some of the future work ideas which we discuss and are working on will be to start looking into language and image pre-training of models where the representations of image and text description is learned in the same shared space. There is work on that. There's an interesting paper clip which explores it, and this is an idea for future exploration. And also, in all this talk, we would have noticed we're only capturing item-to-item relationship, like we're not taking into account any user signals, and that's the idea of experiments. But we can incorporate, user preferences, and Kai had a talk in the morning. So we have those user representations as well, which we can incorporate later on. And by this process and having personal shoppers in store, keep collecting human verified data, it's very valuable. The only reason we can carry out these experiments and compare them is because of the actual human selected data which we had. Yeah, some of the acknowledgements. A colleague of mine, Brandon, he worked on creating the goal test set. For this, he's not here today. And some references. One is, I worked with him on tailoring the experiments. And thank you. And I'm not sure if any questions. Yeah. Any questions?
Hello? Oh, there we go.
Hi.
Hi. Thanks so much for your talk. I'm coming at this from a little bit of a different place because I too work for Loblaws, but not for the digital side, the central side. A question for you about, this happens at Loblaws and a lot of other retailers. We already have an organized taxonomy of products available. So we're showing MCH1 and we have MCH0 and the AH5 system.
Right.
Have you ever been interested to take a look at whether that existing taxonomy is either a good way of verifying your outputs or could be used as an input into deciding substitutions? So for example, we have frozen mangoes and fresh mangoes. Those may be similar in terms of textual similarity, but for example, they would be perhaps not product substitutes that the shopper would be interested in getting, and those two are quite separate in the overall retail taxonomy of how the articles are organized.
Yeah, okay, if I understand it. So yes, we do have, and you would know we have multiple taxonomies too. So in this, and as it's a taxonomy, so it has different hierarchy levels. So my idea is rather than, we can flatten the hierarchy, use those points as well, but we didn't do that because I feel like there's a relation in that taxonomy, okay, center of store, then this, a precedent has to happen for the. I think in this, to your point, how can we just feed categories into this? I think we are in a way because we are doing masking and it's so sometimes the categories get masked certain, and based on the name, the model has to predict the category or vice versa. Does that answer the question? Okay. Oh, there's a hand.
Hey, thanks for the talk, it was great. Just a question about the similarity of products. So I think, if I remember correctly, you're using KNN to find similar products in your 256 or 512 dimensional space. How does that work? What's the distance metric you're using? Yeah, just asking because we deal with similar types of data.
So we're using K nearest neighbors. Since these are dense representations, we're using cosine similarity for both.
Hi, thanks so much for the presentation. I just had a question about how you were weighing the rankings that you got from the vision model and the language model.
Sorry, didn't get the first part.
So what I understood was like you have the language model, which was ranking the similar products, and then you had the vision model as well, like ranking the similar products. Like how were you merging them together?
Oh, I see. Yeah, I think it was So, if we have an item-to-item matrix, we can create a half-triangular matrix where, given a pair of products, what's the similarity? And that entire similarity matrix can be captured as item-by-item matrix. We store that. We do the same for Sinclair. And when a query comes in, we get the similarities from both, weigh them, and generate the final similarity. But in case of generating recommendations, we need to have like n as like 100 recommendations, 10. So in that case, we generate we get the top similar items from Roberta. Once we have that, we get the similarities for those from Sinclair, and then weigh those based on those weights, which are so like if the Roberta similarity is 1, after weight it becomes 0.9, and Sinclair would be weighted based on their weight. And then the final results get re-ranked again. Does that make sense? Oh, since we have 2 models, so it's like, one or the other. So we did a search on 0.1 to 0.9. No, that's a great point. And this is the idea of like before getting these results, we would not know as well. So now we know, and like our decisions would be based on these things. It's not; these are experiments. All of these are not models in production. Okay, thank you. Thanks very much.